In part 1, code requirements and calculation methods, we explained already the minimum reinforcement for brittle failure and crack control with or without specifying a crack width. We also handled the minimum reinforcement due to restraint deformation. In part 1.6, a summary is given for the different methods. The formulas for determining the minimum reinforcement can be subdivided into three large families. You have first brittle failure, then second control, crack control, and restraint deformation. Crack control can be divided into two types, one with a specific crack width specification or without a specific crack width limitation. And then you have a series of formulas only for bending and another series for only of tension. For restraint deformation, it can be based on a graph. The steel stress can be based on a graph, or it can be done by direct calculation. And the last method for restraint deformation is based on a restraining factor, on an epsilon free. The result varies from 165 square millimeters up to 687. It is important to choose the right calculation method. Applying the 8 different formulas to a slab with a thickness varying from 200 to 1000 millimeters, we obtain the following results. On the y-axis, there is the amount of minimum reinforcement. On the x-axis is the slab thickness. First of all, there is a wide scatter in the results. It is important to choose the correct method. Global tension with crack width control, it's like a tension rod. Method 5 gives the highest minimum reinforcement and is almost independent of the slab thickness. Minimum reinforcement for brittle failure, method 1, is proportional to the depth of the slab, and it is the only method that is proportional with the depth of the slab. Using the strain method 8, it results in the lowest amount of reinforcement. Excluding pure tension and using the minimum of method 6 and 7, this results in the following graph. We can see that restraint deformation, which is method 7, is dominant for a slab thickness smaller than 650 millimeters. So most slabs are smaller than 650 millimeters. So restraint deformation will determine your minimum reinforcement and not brittle failure. Brittle failure, method 1, is dominant for sections bigger than 650 millimeters, or for slabs bigger than 650 millimeters. We can do now the same with a crack width restriction of 0.2 millimeters instead of 0.3. So the needed amount of reinforcement increases with almost 50%. Just by stating that the crack width must be 0.2 instead of 0.3 millimeters. Again, we can exclude pure tension and using the minimum of method 6 and 7. And then we can conclude that restraint deformation, method 7, is dominant for slabs smaller than 800 millimeters. And for brittle failure, it is dominant for slabs higher than 800 millimeters.